It's time for me now to get into some of the more complicated topics that are described in my lengthy analysis of variance PDF, the one that's 54 pages that was distributed earlier in the semester. Some of the concepts, if you read through them, uh, the material that's described in the pages, around 40 to 50, they're pretty complex, and without having someone describe to you what it actually means or is doing, it's kind of hard to follow that stuff just reading it straight out. So I want to take a few minutes and describe this to you. You can see that I'm starting here at page 39, and the material here was covered partially in one of my previous videos. You can see what I have here is the familiar psychotherapy and drug data that we've been working on for some time, probably too long. And you see that we have 3 people in each cell. This cell here has both psychotherapy and drugs. This cell only receives psychotherapy. How do we know? We can tell that by the number, or rather the letters up here in the upper right hand corner of each cell. This cell only receives drugs. Psychotherapy is absent. And this cell only receives, well, they don't receive anything. That's the control group. And then I also have the margin means down here. The marginal means indicate the mean for all the people in that column. So the mean here, 6, is the mean of all 6 of these people here, whereas 3 is the mean of all 3 of these people, all 6 of these people here. Over here, for this margin, we're looking at the rows, and this would be the mean of all 6 of these people going this way. Whereas this mean is the mean of all 6 people going this way. And then we have the grand mean. So I've already walked through part of this. Here's the same structure of the design of the cells of the experiment with the cell means inserted instead of the raw numbers. So I'm going to skip past some of this because I've already covered this. One thing to always remember is the relationship of these different types of variability to each other. The sum of squares total gets divided up into the between groups and the within group sum of squares. The between groups is your treatment effect, and the treatment effect in turn gets divided up into columns, rows, and interaction. The sum of column sum of squares plus row sum of squares plus interaction sum of squares will be exactly the same as the between groups. It has to. So remember this layout. Remember this structural layout of the relationship between these different parts of the model. The within groups is the noise, the between groups is the signal, and these are 3 different types of signal down here. The columns, rows, and interaction are 3 different types of signal. When you add them all together, it equals the sum of squares between. The sum of squares between, of course, is used to calculate your one-way ANOVA, and then the column, row, and interaction sum of squares are used when you're computing a factorial ANOVA. And these will give you the main effects of columns and rows and the interaction of columns and rows. Okay, so I'm going to skip past this part where I illustrate the computation of the columns, rows, and interaction. I've already done that in a previous video. But I do want to take a second and take a look at this results table, this summary table that I got from SPSS. We've got a number of different things shown here, including a couple that we don't actually compute by hand, such as what SPSS calls the total. What we compute when we do it by hand is actually the corrected total. And one of the things that I'm going to explain to you is the difference between the total and the corrected total. We see the error term here. That's sum of squares within. It's in SPSS it's called error. And above that we have the interaction of psychotherapy and drugs. And you can see what they do here for interactions. They use the asterisk along with the different variable names. And the asterisk is traditionally used within this context to indicate that you're doing an interaction, that you're reporting an interaction effect. And then there's one other thing here that we don't report, or we don't actually calculate by hand, and that's the intercept. I'll also explain what that's doing there to some extent in a few minutes. So the other parts of the model here look familiar. The corrected model is the between group sum of squares, the column and row sum of squares interaction, the error term, and the what we call the total. So keep that in mind. I'm going to use that as a reference point in a couple of minutes as I get into this next topic. So here's where things start getting really interesting. At page 46, I've got this table 1, and the concepts here, the concepts that I'm relating to you here, are taken from Rosenthal and Rosnow's textbook, The Essentials of Behavioral Science. Their description is really rather good. I took the class with Dr. Rosnow to learn this material, and even then, when I read it several times, it took me a while, but now I believe I have a pretty good grasp on it. So what I've done here, and I've arranged these tables in a slightly different way than what Rosenthal and Rosnow do. What I've done here is I've taken the cell means for my 2x2 factorial ANOVA. So the group that got both psychotherapy and drugs, that group's mean is 8. The group that only got drugs has a mean of 4. The group that only got psychotherapy has a mean of 4, and the control group has a mean of 2. Now, one way to think about what we're looking at here is that the group mean, if we look at this number here, this number 8, the group mean can be separated out into its different parts. If you take 8, which is that the cell mean or group mean for the PD group, subtract the grand mean. We know that the grand mean of all these 12 scores is 4.5. If you subtract the grand mean from 8, and then also subtract the row mean, and then also subtract the column effect, what you're left with is a very small number, which is 0.5. So I guess another way to think about it is if you took these three and added them up, 4.5 plus 1.5 would be 6, and then if you added another 1.5, that would be 7.5. So in other words, what we're doing is we're taking the group mean of 8 and we're subtracting 7.5 from that. That's just adding up these different parts here. 4.5 plus 1.5 plus 1.5 is 7.5. So now, when we remove these three things, the grand mean, the row effect, and the column effect, from this cell, where the mean is 8, what we're left with is 0.5. Where did these things come from? Where did these two come from? The row effects and column effects. If I go back up a few pages, we have the answer. Maybe I should have rearranged things for this particular video. But here we go. So this is at the bottom of page 39. That's your row effect for the people who got drugs. They get a bonus to their baseline score of 1.5 on average. This is your column effect for the people who got psychotherapy. They get, on average, a bonus of 1.5 above their baseline. What is the baseline? The baseline is the grand mean. The grand mean serves as the baseline. So what we're talking about here is to what extent, on average, do these different treatments have an impact on scores on average relative to the baseline. And this is what we're looking at here. So this particular table represents the cell means after removing the baseline. So I took 8 and subtracted 4.5. That's where this comes from. And then this is what we're looking at here is the mean of what's in these two cells. So if I take 3.5, subtract 0.5, and so that's 3, and then divide that by 2 because I've got two cells here, what I'm left with is an average of positive 1.5. And if you look at the individual scores, you'll find that they're on average, the people in this row are on average 1.5 points above the grand mean. So this is the benefit. This is literally the average benefit of getting drugs. This is literally the average benefit of getting psychotherapy. And so that you can see that there's a deficit for people who don't receive any of these. They have very low scores, negative 2.5 on average, below the baseline. The actual mean of that cell is 2 on whatever scale this is being measured on. And 2, the value of 2 is 2.5 units below the grand mean. So that's what we're talking about here, that the people who don't receive any treatment are that they have scores below average. I guess higher scores are better. So now let's go forward again to that table that I just had up there, where I started to decompose the different scores, the different mean scores. Here we go. So that is quite literally what this table is illustrating. If you take the cell mean for any particular group, in this first case the cell mean is 8, if you subtract the baseline from it, subtract 4.5, and then also subtract the row effect and subtract the column effect, then what you're left with is the interaction effect. The interaction is what's left after you take the other parts out. And a lot of people don't really understand how that works. In fact, when I was taking these methods classes with Ralph Rosnow at Temple University back in the 1990s, he was having a debate in one of the research methods journals of the APA with some other established researchers, and they found it impossible to follow the logic here. Apparently, Rosnow kept explaining the issues in print, and they kept not quite following what Rosnow was saying. And I think it's a different way of thinking about the structure of ANOVA. Usually when people talk about analysis of variance, it's with a regression model. So maybe that's part of the disconnect, but I think this is a nice way to envision what's going on here. The interaction effect is what's left after you, I wish I could highlight just that section here, but in a PDF I can't do that. The interaction is what's left after you take these other components out. For the control group, you start at 2, you subtract 4.5, but then you have to subtract a negative 1.5 because they're already below the mean. And so basically what you're doing is instead of subtracting a negative, you're actually adding it. So it would be 4.5. So you start with 2, subtract 4.5, now you have a negative 2.5, but then you add 1.5, and then you add another 1.5, and what you're left with is a positive 0.5. So that's how this table works with the negative signs and the minus signs, just in case you found that hard to follow. Now, here's a different way of lining the same numbers up, and the way that this one works is like this. You can think of every individual cell mean or group mean as being equal to each of these different components. So the first table I showed how we get to this part, which is not intuitive because it's not in that table at the bottom of page 39. So I needed to explain where these numbers right here came from, the positive 0.5s and the negative 0.5s. If you did examine the diagonals in the 2x2 table, you'd be able to get these same numbers. But anyway, so now that I've established where these numbers come from, we can take a look at the table in a rearranged setup such that each cell mean is equal to the different components seen here. 8 equals 4.5 plus 1.5 plus 1.5 plus 0.5. And do the simple arithmetic and you find that same answer. And moving down to the last one, 2 equals 4.5 plus a minus 1.5 plus a minus, or I should say negative 1.5 plus a positive 0.5, and so forth. Okay, so that's how we can think about the individual cell means. Each of these means is made up of these different parts: a baseline, a row effect, a column effect, and an interaction effect. And so we already kind of know that. Now let's look at the interaction more closely. Here I've mapped out the interactions from this table, from here, these scores, the positive and negative 0.5s, and so that we can see where they're lining up. And you can see that the residuals are zeros. You can also see that each diagonal is either positive, like this going across here, that's a diagonal. That's positive, while this one is negative. You see that this diagonal is negative 0.5. One of the things that Rosenthal had difficulty explaining to people, and I usually do this in class writing on the board, and so it's kind of hard to do it verbally here, is that in a 2x2 design, you always get a structure like this for the interaction. You always get a diagonal that's crossed like this. It may not be perfectly crossed, but the numbers have to cancel out to 0. That is to say, the distance from here to here may not be the same as the distance from here to here. This is a 1-unit distance between positive 0.5 and negative 0.5. That's a 1-unit distance in whatever metric this is. And so is this one. That's 1 unit of distance. It's possible to have different distances between these diagonals, but they have to cross. If there's any non-zero interaction effect in your ANOVA, you're going to have some numbers in these diagonals that are not zero. So I'll just skip past that because I don't think I can really explain that verbally here any better than that. But let's look at the individual scores. The individual scores, the same way that we looked at the group means and decomposed the group means into their constituent parts, we can do the same thing with individual scores. So these 3 scores right here, again, I can't highlight them all, but the 9, 8, 7, these 3 scores here are all in the PD group, and we can take each individual score. Let's start with the first one. The score of 9 is composed of the baseline, which is the grand mean. Some people are going to be a little higher and some people a little lower than the grand mean. And that's really why it's a baseline. You'll have an equal amount of distance in the deviation scores above and below the grand mean overall. When you average them out, they have to add up to 0. But so we take the score of 9. The score of 9 is composed of 4.5 as its baseline, plus its row effect, which is 1.5, plus its column effect, which is 1.5, plus its interaction effect, which I illustrated how we got that. That's 0.5. That comes to 8. 4.5 plus 1.5 plus 1.5 plus 0.5 is 8. Well, what's left over? Because the raw score is 9. We have an error over here. That's our error of estimate. In other words, that goes into the error term of the analysis of variance. This is what we're talking about. Every individual in your experiment is going to have a value on the dependent variable that is composed of its baseline plus whatever treatment effects it gets, plus whatever interaction of those treatment effects happens to be there, plus error of estimate. And the error of estimate, I've said this in class the times that we have met. I've said this more than once. Error of estimate is simply that some people score higher or lower on whatever it is that you're measuring due to nothing that's under your control. It's just individual, unique, random characteristic error. And this is where it shows up, that some people are higher or some people are lower on your dependent variable, and we don't know why. Another way to think about that is that this particular group is predicted to have a value of 8. That is the group's mean score. and this person had a score that's 1 unit above the predicted value for that group. Now the second individual here does have a score of 8, and we can see that that's made up of that person's baseline for the entire experiment, the treatment effect for rows, plus the treatment effect for columns, plus the interaction of those two treatment effects of getting both of them. There's an interaction effect, you get a little bit of a bump. And then plus 0, because 4.5 plus 1.5 plus 1.5 plus 0.5 is 8. There's nothing left over for the error. In other words, this person right here with a score of 8 behaved perfectly as predicted according to the statistical model that we have set up here. There's no error. Now that doesn't actually ever happen in real life. There's always error. But it's a nice illustration. So for every individual here, let's take one from the drugs group, this person here, just to show a different pattern. This person's score of 5 is composed of the baseline for the experiment, which is 4.5, plus 1.5. Well, now we've got too much, because 4.5 plus 1.5 is 6. Well, the person has a score of 5. Well, we lose that 1.5 over here, because that person did not get psychotherapy, which is the column effect. So they get a deficit instead of a benefit here. They get a deficit of 1.5. And there's also the interaction effect over here is a negative as well. So what we end up with is 4.5 plus 1.5 is 6. Minus 1.5 is we're back to 4.5. Minus 0.5 we're at 4. And so we have a positive 1 over here, which represents the error of estimate based on that individual's position relative to where we thought that person was going to be. So that's what this is doing. You can see the different treatment effects here and how they line up, as well as the error. And there's more error down here for some of the people than for others. Okay, so I hope that explains the issue fairly well. That every single individual can be thought of as, I should say it this way, every single individual's dependent variable score is the sum of the different components of the model plus error of estimate. And usually in real life experiments you have much higher error than what we have here. Now at the bottom of the table we have sum of x squared. That's this sum of x squared. And if we have the raw scores, if we square all of these raw scores and add them up, we get 320. Well, 320 sounds kind of familiar. I don't know if you caught that, but if we go back and look at the ANOVA summary table, let's go back a few pages. 320 shows up right here. That's the sum of the squared values for all the raw scores. That's what that is. But that's not a very useful thing for us. So we don't actually use that for anything. But it's included within the SPSS output as the total sum of squares. Again, that's the sum of the squared values of the raw scores right here. If we took each one of these, squared them, and added them up, that would be this number. And then the grand mean, if we take the grand mean of 4.5 squared and add them up for every individual in here, we get 243. And so let's go back to the ANOVA summary table. And lo and behold, here's 243. That's the intercept. In other words, that's the baseline. So where does 77 come from here? If you take 320, subtract 243, you have 77. And if you take this number, subtract the baseline, you have 77. So this is the squared value of all of the raw scores. This is the squared value of the baseline. Well, it really is the baseline. Take the 320, subtract the baseline, and what you're left with is the part that's actually attributable to the treatment effects and the non-treatment effect, the noise. So the noise is here, the error. Okay, so now let's go back here. If you go to the ANOVA summary table for the sum of squares for the drugs, it's 27. If you go to the ANOVA summary table for the sum of squares of psychotherapy, it's 27. The interaction sum of squares is here, and the noise, otherwise known as error, or sum of squares within, is right here. So all of these different parts work together. And there's kind of a very interesting and neat way in which they work together. It's a very clever arrangement. And you really have to hand it to Fisher, Ronald Fisher, who developed this method. It's very clever the way that these things work together. Okay, so now we can think of it this way: any individual score is equal to the grand mean plus the row effect plus the column effect plus the interaction effect plus error. One other point here that I'd like to cover, and then I can stop this particular instructional video. At page 48, I have a little bit of a discussion of eta squared. Eta, ETA, refers to the Greek letter eta, which is used to specify the amount of variability or sum of squares in any given part of the model. And so this is the total amount of sum of squares that's within our model, not based on the baseline and not based on the total squared raw scores. If we take any one of these individual components and divide it by 77, then we have the proportion. So the drug effect, the row effect, has sum of squares of 27. If we take 27 divided by 77, we get a proportion of 0.35. In other words, the drug main effect is explaining 35% of what's going on inside this model. The psychotherapy main effect also has a sum of squares of 27. And again, 27 divided by 77 is 0.35. Psychotherapy is explaining 35% of what's going on in this model. Those are really big effects, by the way. The interaction effect is doing almost nothing, and then the noise has 26%, and you can see that they all add up to 1. So that's eta squared. Now, when you ask SPSS for the effect size, what it gives you is partial eta squared. And you can see that the numbers here are different. I don't want to, in this video, I don't want to go into the difference here. I don't think it's that important for our purposes today. But I wanted to point out to you that what we're looking at here is ratio of treatment effect or non-treatment effect to the total effect, and that these have to add up to 1. When we're talking about partial eta squares, it's like a partial correlation, which I'll get into in the next section when I start recording videos on correlations, but they do not all add up to 0. And I think the rule of the rule of thumb to use here is simply that be careful which one you're talking about, because partial eta squares sum to a value greater than 1. You can see that if we added these up here, they would add up to a value greater than 1. So there is a difference between eta squared and partial eta squared. I like eta squared, really, but eta squared only works within the reference point of the ANOVA summary table itself. I know that's not a very good description of it, but it's something to think about. Anyway, these are effect sizes. You can think of these as effect sizes, but I'll have more to say about that in a different video. Okay, so that's what I have today. Thank you.